Okay, let's go ahead and get started. So last time we started discussion about assembly or x86, where I totally took these slides with full permission actually. Yeah. And we started on these slides about how to program on x86, and then we got sidetracked because we had to do 2's complement. And we talked about the 2's complement, which was a way to encode numbers. Anyone remember the advantage of 2's complement?
It's better.
It depends.
That's how
No.
I say.
Good try. Good try.
You don't have to deal with negatives.
Well, right. You don't have to deal with negatives. Namely, additionally, you still have negatives, and your negative is determined by the first bit, whether it's positive or negative.
But you're always adding.
But you're always adding, so you never have to create a subtraction circuit. So your adder does subtraction, because subtraction is really just addition's tricky friend. That's all there is to it. Yes?
I remember seeing only examples of like negatives that are like between like -1 and like negative like 999.
Sure.
Does it like scale up?
Oh yeah. The more bits you have, the more it scales.
Okay.
So that's why the 32-bit number goes from roughly positive 2 billion to negative 2 billion. And then the 64-bit one is something even much larger. All right. So again, I took these slides from permission. There's the license. We gave those people some extra credit. Sure. What? But no money.
Can I get extra credit?
Sure. What would you like?
All of it.
All of it? All right. I give you 100 meaningless points.
Yay, yay.
These are West dollars.
West dollars?
West dollars.
Yes.
1 point of your grade. Like shoot ducks.
All
1,000
right.
West dollars is 1 fruit buck. And
Fruit
1,000
buck.
fruit bucks is 1 point.
It's true.
All right.
How much is this thing?
So this class is going to focus on 32-bit x86, just for simplicity at this moment. These slides don't go through floating point or the 16 or 64-bit ones, but we're going to, but we might go into that later, and by might I mean most likely we will. We're not going to do any complicated or rare 32-bit instructions. There are some really funny ones. My favorite is string copy. There's just one instruction that does string copy all by itself. And we're not going to go through, well, these slides aren't going to go through the pipeline, caching, alternate modes of operation, virtualization, etc. But obviously we're going to cover that in this class. So he talks about how this guy loves to do the wall of text, I've learned in life. So he says, I hope this class is great. Here's a quick agenda. Part 1, which hopefully we'll finish today, is architecture introduction, and we'll talk about Linux tooling and some instructions. And then next we'll do some more about assembly and maybe, choose your own adventure. Anyone want to focus on anything in particular with assembly? Or you have no idea because we haven't decided what assembly really is?
Second one.
That one?
Yeah, the latter.
The ladder? I do like ladders. All right, good old miscellaneous. If you have questions, ask. I'm a benevolent dictator. And x86 because it went 8086, 186, 286, 386, et cetera, et cetera. So what you're going to learn, this program. All right. I didn't even code this program up in assembly. It looks like this. What are you talking about? It just went from that to that. It's not even that many more lines of code.
That's great work.
What?
I don't think it's the amount of lines that we're worried about.
Yeah, it's these are simpler.
Everything else.
But you just push EDP on the stack. You move EDP over to ESP. You push the offset of hello world, which is the string, so you can push where that thing is, where the string is. You call printf so it knows that it needs to go to hello world. It prints it off. When it comes back, you need to decrement the stack pointer because you just came back from it. You move that number into EAX so you can tell that this program is going to return 1, 2, 3, 4 in hex. You pop it, and then you return.
What's EDP and ESP?
Oh, those are registers. Did we not go through the registers? No? Oh, okay. Wait, we did, and all of y'all forgot about it?
Probably.
It is the LC64 register.
Oh, yes. All right. By the way, this piece of code here is the same as that piece of code there.
I like the other one better.
What's
You-
the thing?
you like-
I like the dress.
I like the original
label or something.
So there's this, the original Flame Wars.
The things on the left, like they said text and all that, are those?
Oh,
like
so that's the
addresses?
.text section at that memory address because your programmer resides in memory. So notice that the push instruction is 1 byte.
Yeah.
The move instruction is 2 bytes. The next push instruction is wow.
So
4
is it
bytes.
telling you to go to a specific memory address?
No, these are where these instructions reside in memory.
Those happen to be, so do you have to have that label on?
No.
Because I did you just specifying?
Yeah, they're just specifying it too.
Okay.
Yeah, so the part on the left doesn't matter,
Okay, that's all right.
except for this main thing does.
Okay.
It's the same as that. We'll go through this a little more. The same as this one. This is the Mac version. But it boils down to you're pushing some offset, you're calling printf, you're popping it because you're coming back from the function, you're moving the your return value, and then you return in. Great. Ooh, disassemble die to pro. Sweet. By one measure, only 14 assembly instructions account for 90% of the code, which is great because that means we don't have to cover all hundreds of the instructions that are possibly out there. We can focus on less than 20 and cover the vast majority of what you'd be reading if you decide to go down the path of assembly writer, which, by the way, is a well-paid job if you wish to pursue it. Okay, so refresh your data types. So a character is 1 byte, that's 0 to 7. A short, which is 2 characters or 2 bytes, you have your low byte and your high byte inside of it. Keep in mind that it's important to think of a short as a low byte and a high byte because that will pop up. An int or a long or a 32-bit long will have a high word and a low word. Now, why they call it word when it should be the high short and the low short? Don't come talk. I don't know. They decided to do this. This is why x86 is confusing. Because it really should just be called a double short, and then you have the low short and high short. But they decide to make things more confusing because that's how life is. And then a double or a long long or just a 64-bit long will be a low double word or a low double word or and a high double word, also known as a quad word. Sure. And to make everything super confusing, a word in x86 is 16-bit, a word in LC64 is 32 bits, yes.
So is like the high and low just like the range?
Yeah, so the upper half and the lower half.
Okay.
And then I guess the long double, which is the double quad word. Would that be the awkward? Awkward. That's great. All right. So quick refresher on, let's see, decimal, binary, and hexadecimal. So on your left are the decimal numbers. Hey, look, they go from 0 to 15. The binary versions. Notice we end the binary version with a B to signify that it's binary. And then the hex, we like to precede it with the 0x. Sometimes you'll see it end with an H. Just like this ends with a B, it might end with an H. This is hopefully, excuse me. This is hopefully a refresher for everyone. Yes.
On our earlier slides, we could have written out binary as B apostrophe the sequence of numbers.
For Verilog, yes.
Okay, so that's Verilog code. This is
Assembly code.
assembly code.
So yeah, we're switching languages again. You have Verilog, which specifies your processor, and you have assembly, which is going to be the instructions that you're going to send to your processor.
Okay.
All right? They're
Are we
all
using-
different.
Are we using a specific assembler for?
We're going to be using NASM, N-A-S-M. I'll get to that soon. That is that version uses the Intel coding style. Don't use GAS, which is the GNU assembler. That has a different coding style that you're probably going to not enjoy.
Sorry for jumping ahead. I was just curious.
Not a problem. And then, of course, negative numbers. I think this is where we left off. Where we were talking about 2's complement.
Hey.
Yeah. So number in binary on the left is 1. Bless you again.
Bless your face.
1's complement would be that, but 2's complement is all the 1s. If this is confusing, just ignore the middle column because no one does 1's complement. Well, hold on. No one does 1's complement for integers because that's just dumb. It's useless. So just worry about 2's complement and our number. If this is not familiar, please refresh the slides from last class and, of course, the lecture. All right. So notice the easiest way to look is if the first bit is on. 7, by the way, is 0, 1, 1, 1. So that first bit is not on, so that's a positive number. And of course, all f's would be a negative number. Oh, hey, cool, there's the range. I didn't see that. From 1 to 0, x, f, blah, 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 blah. And the negatives are from 8 all the way up to there. Sweet. Nice. This is the smallest number that can be represented. Or the largest negative. How am I supposed to pronounce that? Which way does that go? You know, the negative with the most digits. Is that smaller or larger than -1? It's smaller.
It's the smallest number, but the largest negative value.
Yeah, exactly. See how confusing that is? Man, that's confusing.
No.
All right, good old CISC versus RISC. Is this new?
Yes.
All right, here we go. So CISC stands for Complex Instruction Set something or another. Oh, computer. Whew. Huh, I'm glad I wrote it down. So Intel, well, that's a lie. x86 is CISC. I need to fix that right now. Perfect. x86 is CISC. Many very special purpose instructions that you'll never see and a given compiler may never use. You just need to know how to use the manual. All right. The idea with CISC is that you can do a lot of very complex things inside of an instruction. Bless you. And because of that, you have variable length instructions from 1 byte to 17 bytes. Although the 17-byte instruction is rare, you're going to see a lot that range from about 2 to 6 all over the place. The other major architecture is RISC, which is the reduced instruction set architecture. Instead of having complex instructions, you're going to have very simple instructions, aka add or move or if, something like that. While your CISC may be, let's go and code string copy or string compare inside of an instruction, which is a whole set of instructions you need to do in order to complete that. So, typically, also they usually have more registers and fixed size instructions and far fewer instructions. And some examples, PowerPC, ARM, Spark, and MIPS. In fact, I think x86 is the only CISC one out there. Yep. Because of course it has to be different. Just like Windows. All right, hey, we talked about Indian, didn't we? All right,
Yes.
great. Little Indian, big Indian. I actually like this picture in the slide because I think it really, really does help. So, big Indian. Oh, again, let me roll back in case we missed something. Little Indian is, they did Intel again? The reason why this is wrong is because Intel's come up with other architectures. Besides Little Indian, they came up with the Itanium, which is a little different, but whatever. x86 is Little Indian, and this is the way you think about storing numbers naturally. The least significant byte is of a word or larger is stored at the lowest address. Big Indian has it the other way around, and basically x86 did the Little Indian, which is the intuitive way, and everyone else decided to go Big Indian because that's the way networks decided to do it. Although some architectures are called bi-Indian, which means they can flip their Indianness.
Okay. So they crack it in the middle.
No, I'm trying not to say they swing both ways. That's a better way of putting this.
They can't make a decision.
They can't make it, well, but they do one or the other. They don't take the middle road. They don't crack their egg in the middle. They either crack it on the small end or the big
Yeah, I'll
end.
say it for you, they're swingers.
They're swingers,
They're
sure.
flip-flops.
They're flip-flops. There we go. What's the appropriate PC way to say this? I don't even know.
Well, I would say flexible or.
They're flexible.
I think the
This is just going downhill.
There's so many different.
I mean,
They're
you're the one with the
They're
mind
not
of the
faithful
gutter
to
this
one
time,
Indian.
so.
What's that?
They're not faithful to one Indian.
They're not faithful. Yeah, so they're not faithful to the crown or to the rebels. Okay. Big Indian. Here we go. So notice that the memory addresses are going from the bottom up. And so with the let's go little Indian. The smallest is at the lowest memory address. Up here, the smallest is at the highest memory address. So when you want to, the reason for this, when you want to, read the start of it, yeah, you start here and go down. All right. Whew. So registers are small memory storage areas built into the processors, still volatile memory. A register is going to be your flip-flop that we've been talking about so far. And x86 has 8 general purpose registers plus an instruction pointer plus a bunch of other things that we're not going to get to. And so on x86 32-bit or x86 that we're focusing on, they are 32-bit long. And 64, hey look, they're 64 bits long. So each register in our version, because we're doing 32-bit, is 32 bits. And each register on the 64-bit version is 64 bits long. All right, and again, a register is just a collection of flip-flops. How many? Depends on your bitness. All right, let's see. I think at this point, it's good to jump over and see what we're dealing with. Let's go to O3 functions. Excuse me. I'll open up function.assembly. What is this doing? Well, here's this equivalent C code right here. We include apparently nothing. There, I'll fix that. We include standard I/O. We create a function called sub that just returns beef. This is very common. You can look these up. There's a lot of them. My other favorite one is what? Dead Cafe. And so you got main, and then it's just going to print off beef. Actually, it prints off sub. So let's fix that. There we go. EAX equals sub. So this should just print off EAX equals beef, or whatever the beef representation is. And D, actually down here, it's a %X, I just noticed. Wow, who wrote these comments? Oh man, all right, much better. So that's the C code that we are translating into assembly. You can, oh, is this easy to see or is this real hard to see from back there?
There's words on the screen.
There are words on the screen.
I'm good. Is that stuff up there in comments?
I can't tell if it's me or not.
How's that?
And clear.
Let's see, can I make the font bigger? Hey, look at that. Oh, that's
They're all
beautiful.
featured. Gorgeous.
Wow, this is why I don't use GUIs.
Is that slider there? No.
All right, so where's the button to make it bigger?
Use Control Plus.
Control plus. That did not work.
My shame.
There's no view, is there? No?
I don't know. I don't use GUIs.
Or not window.
That changes the size of the window.
Yeah, that changes the size. You know we're not pressing that button.
Tripod. Is it one of the little symbols?
One of the symbols? I don't think so. So you said file? No, it's not any of that. It's got to be under edit.
Oh, this is the GUI version of that? This is
Yeah,
all-
exactly. It sounds terrible.
Colors
Why would you
spell
do
color.
this? What's that?
They spell color the British way.
Yeah,
My shame.
not the American way.
Merc. This is awful.
This really is
Remind me
terrible.
to never use GUI.
GVim? Yeah, GVim.
They took
Okay.
a great thing and then just made it terrible.
It really did.
If you're gonna make something GUI, at least make it good.
Color test? We can run a color test? All right, I have no idea how to increase the size. Maybe we can do gedit. I wonder what that's going to do. Oh, but now you don't have highlighting, so you have no idea what's actual code and comments.
To change the theme. Theme that we'd use for.
Deleted? All right, cool. So how's that for people back there who have a hard time seeing? Fine. All right, someone go online and figure out how in GVim to increase the size. We'll figure it out eventually. Okay. So I'm going to read this code from the top down, and then we're going to go through the slides which basically explain it, and then we're going to come back to the code, and then it will hopefully all make sense. All right? So if I read it the first time and none of it makes sense, that's fine. I just want to give you an overview of where we're going, explain all the bits, and then come back and review it. All right, so anything that begins with a semicolon is a comment. So you can just ignore that. Extern printf, this means that there's going to be a function called printf that's external to this assembly file that that I want to be able to call. Yes?
Found out how to change the font size. It is a command :set GUI font equals and then size.
Oh, okay, there's probably a space between set and GUI.
Yeah.
They didn't like that. Set GUI font. Did I type that right?
Should be.
Invalid fonts.
You need to put the name of the font, colon, then like the size.
Yeah, what font do we have? Do you have an example?
Mine says Gonzalez.
Gonzalez?
All those
How about terminal?
Numerals.
Terminal?
Or Arial.
Yeah, you can try Arial.
Yeah, don't, as a father, it's really hard to watch that movie. Arial what?
:H and a number.
I think there needs to be a space. No.
I love this.
I love how the very simple things are now
I
impossible.
love how this is GUI, but you still have
Did
to
you,
type
You're
it.
an expert.
did you capitalize the A in Arial?
No.
It is cap sensitive.
No. Well, why don't you figure it out? So external printf, there's going to be a printf that's external to this assembly file that we want to link against. We're going to call the next section data. Let me move this window over since we're getting it cut off on the screen. There we go. Section data means that these are going to be the static variables of your program. So you remember from hopefully previous courses that you can have static variables, aka constants or global constant variables. That's where you declare it here. And I'm going to declare FMT, which is going to be a label. So I'm going to label this constant, or this static variable FMT. It's going to be a double byte, and it's actually going to be a string EAX equals %x. And this is an array notation. So after the %x, we're going to have a 10, which by the way stands for \n, followed by a 0, which stands for the null terminator. The reason you write it this way is because assembly, if you try and encode it in assembly, sometimes that doesn't work out as best. So if you just want to tack on some extra values, you just use a comma and it becomes an array. So this is an array of double bytes, basically, FMT, and it's going to point to this string. All right. So we have FMT, that's a string that you want to send to printf. Section text, .text is where you're going to put your code. These are the assembly functions. The first thing you want to do is call global.main. What this is saying is I want this main label, main's not a function, it's a label right now, to be viewable to anyone, to everyone that's trying to link against my file. This is important because if you don't call it label, call it global, the linker or the assembler may optimize out your function, and then you won't have this label in be external to the rest of the program. So you must label any label, well, that's a lot of labeling, that you wish other programs to see. Specifically, why do we want main to be global? Well, when we go to link it, they need to know where we're starting a program, and by convention, GCC starts it where main is, so I'm going to call it global main. All right, next comes sub label. This is a label, we're going to call it sub. This is actually a subtraction function. And we're going to push EBP, so we're going to push the EBP register on the stack. What that does is it allocates 4 bytes, shows the contents of EBP on those 4 bytes in main memory, and automatically increases the stack pointer. We're going to then take EBP and push it to ESP, which is a stack pointer. We're going to copy beef over to EAX, and then we're going to pop EBP, because that's what you do when you're done with your function, so we're done messing around with any temporary variables. Why did we do all that work with the pushing and the popping? I know that doesn't make much sense, but that is a convention that we have chosen when we use functions in order to set up temporary variables of the function. Whew. So now we go to main, which does happen to be a function. We're going to again push EBP to set up the stack frame, and of course move EBP to ESP so we know where our starting stack is. And then we call sub. So this is calling a function. What function is it calling? Well, it's calling where the sub label resides. So the linker will automatically know to jump up to sub and then start executing at this instruction. And when you call ret, which is return, you'll return from that function. Now when we want to call printf, you need to set up the call to printf because it has multiple arguments. First, you want to push EAX on the stack because that is what printf is going to look at when it's called. And we also want to push the format because what we're passing to printf, if you look, is this string right here followed by the return value of sub. So we need to push those two. Notice that the order is important because we pushed them what looks to be in reverse order. Well, that's because when the function calls, its first parameter is the first thing it sees previous, followed by the second things it sees. So we want to push those values on the stack. We got to push the last one first and then the next one afterwards. Then we call printf. Now, this is a little confusing, but we need to update the ESP by 8 bytes. The reason for that is because we pushed twice. And when we push twice, we push two things that have 4 bytes. So we need to subtract those 4 bytes from our stack pointer. You can notice right there that we're adding them, not subtracting them. That's because the stack on x86 grows in reverse. So in order to shrink the stack, you add 8. Then we want to exit cleanly. So we're going to again take ESP and move it back to EBP. That's because in case someone called main, they'll have the right value. We will pop EBP from the stack, aka we're doing the inverse of what we did up here. We will move 0 to EAX to signify that we have no error, and then we return. All right, everyone got that? Cool. Well, let's go explain it again. So you notice that we had some registers running around there, EAX, EBX, ECX, EDX. Well, those registers are, that's where we store our scratch pad. I like to call it a scratch pad or a temporary memory. So we're going to follow Intel's suggestion to compiler writers and assembly hardcoders or hand coders. And we're going to follow what they tell us we should be using for each register. It's important to note you may use your registers for different things if you wish, but you must be consistent, otherwise you're going to run into a lot of problems when you write assembly. All right, so EAX, we're going to just store function return values. EDX, we are probably not going to use for this class, and that's what the base pointer for the data section, sure, whatever. ECX we use for counter for string and loop operations, aka int I equals whatever. And then EDX we usually use for an IO pointer. We're not going to mess with that, at least not right now. ESI, source pointer for string operation, EDI for, was it destination? ESP, which you're going to see a lot, is the stack pointer. EBP is a stack frame based pointer. I really hope these slides go and explain the difference between the two. Most of the time you need to worry about the stack pointer and just keep the EBP updated correctly. And the EIP is a pointer to the next instruction to execute, aka the instruction pointer. Inside of our LC64, I called this the program counter. In x86, that had to be different, so they called it the EIP. Every other architecture calls this the program counter. Okay, is that really the next slide? Oh, wall of text. All right, these are conventions. These are not something that the architecture enforces. This is something that as long as you follow, things are going to be good. If you deviate, you're going to be sad. So call or save instructions. So EAX, EDX, ECX. If the caller has anything in the registers that it cares about, the caller is in charge of saving the values before a call to a subroutine and restoring the values after the caller returns. In other words, if you're calling a function, the function will have full rights to overwrite those 3 registers all at once without trying to save it off. Which means that before you call a function, if you want to preserve the values in those, you need to save them before you call the function and then restore them when you come back from a function. Because a function is, by convention, allowed to overwrite those. The call, save, EBP, EBX, ESI, and EDI, that's when you are called. If you're going to manipulate those registers, you need to restore them when you're done, because anyone that calls you is going to assume that those registers are correct. So it is your job, if you use them, to put them back. All right. This is convention. We could have completely flipped those registers if we wanted to, but this is the convention we're going to stick with. In other words, if you have information EX, EDX, and ECX, and you're about ready to call a function, you need to save them off. On the flip side, if you're being called and you're going to manipulate the EBD, EBX, ESI, and EDI, you need to save those and restore them on exit of your function. So you can hopefully see that when we call the function, notice that it was going to modify EBP and ESP. That's why it basically pushed them, and then it popped it afterwards to restore it. Simple function, it doesn't do other things, but that is how it is. That's how it is. We didn't save EAX here because we didn't do anything with EAX yet, but we definitely will in some later programs. Okay. Whew. What is that in the background that's watermarked? Can you all see that?
Mm-hmm.
All right. This gets confusing. So, with x86 32-bit, your EAX register can be accessed, or each register can be accessed in multiple ways. You can, first off, if you want to access the entire 32 bits, it's EAX. If you wish to access the lower 16 bits, it's called AX. If you wish to access the lower 8 bits, it's AL. And if you wish to access not the lowest 8 bits, but the set of 8 bits above that, the second to last 8 bits, it's called AH. You got that?
Sure.
Sure. They're just dividing up what you can see. I don't know if this helps any. So the entire, let's go restart. So the entire thing is EAX. The middle half of it is just AX. This section right here is called A lower, and this section right here is called AH. So if you load in, I wrote in a Y. So if you load in EAX, you can access the first 8 bits with AL, the second 8 bits with AH, or the lower 16 bits with AX. Those are all different ways to access the parts of your register. A little better?
A little bit.
A little better.
Not enough for me to do any of this myself, but enough.
Oh, don't worry, you'll have plenty of practice.
Yay.
And if this was the next semester, we would actually start with assembly. Actually, we'd start with finite state automata, go to assembly. This would all be way easier to understand, and then go continue with what we've been doing beforehand, and not have to do as much Boolean algebra. By the way, you can do the same thing with ECX. You just call them CX, CL, and CH. Hey, look, EDX, same thing, and EBX as well. Any questions, comments, screams?
What is the reserved area for each of those? Can we not access those with?
Right. So reserved means that Intel, or I shouldn't say Intel. The x86 designers say that if you load something into EAX, the upper half is reserved for the hardware to do with as it pleases. If you load into the entire EAX, then you get all the bits.
Oh, so that's kind of like data structures. That's kind of like the reserved empty memory.
Yes.
Except that the reserved empty memories for hardware to access.
mess- yeah.
Instead of us to like expand into.
Right, but that's only exists when you're doing 16 or 8-bit operations, not when you're doing 32 bits. It's really an artifact. I don't know if they actually do anything with the reserved, because Intel doesn't give me their architecture, but I mean they could. I don't know what they would do.
I mean, I don't think it's probably that big at this point, but it probably still needs hardware to like access it, or like maybe just to run BIOS even.
Oh no, BIOS is something different. BIOS is another operating system.
I know, I'm getting stuff mixed up, but it probably has something to do with like accessing the data, but it's probably really minimal.
Okay. All this is saying is you don't get this. If you're accessing, if you load an AX, AH, or AL, you don't get the top 16 bits. Don't mess with them. We have no guarantee about what those data bits are. So you leave those alone. That's all this is saying. If you load into EAX, of course, you get all 32 bits. That's all that's saying. So on the other hand, ESP, EBP, and ESI, EDI, and EIP, you don't get the low and the high. You just get the 16-bit, the lower 16 bits. And that's all. All right, great. The E flags. The E flags registers hold many single-bit flags. We'll only ask you to remember the following. You have the 0 flag. Whew. Set if the result of some instruction is 0, clear otherwise. Huh. What instruction do you think that is?
No.
You're on the right track. So which instruction from LC64 was that? Do you remember? You're on the right track. You're so close.
I know.
Any
I
guesses?
remember, but I don't remember what it's called.
What did it do?
It's the. Isn't that the one that sets the program or the counter?
No, the program counter, that's with that's jump address. But
Okay.
what is the jump address based on?
Compare.
Yes, compare. So similar to compare, you have the 0 flag, which signifies what the last compare operation result was. And there's also the sign flag. Oh. There are a lot of flags to be used. There are tons of them. And if you go into architecture, you'll probably start learning all these at some point. But for this class, we only need to stick with these two. All right, your first x86 instruction. I love how they call it the NOP, even though it's N-O-O-P. It's the NOOP, which means no operation, no registers, no values, no nothing. It's really just to add some bytes to your program to pad align bytes or delay time. Bad guys use it to make simple exploits more reliable. That's a fact. So that's another class. Hey, maybe we'll get to that. That'd be great. But it's very common for once they get something working and they need to delay the CPU from doing something else, they'll just throw in a ton of no-ops. Very common. And apparently they found out that no-op doesn't actually exist in x86. By the way, this is very common, that the instructions you write are not the actual instructions that the hardware uses. What no-op translates into is exchange the EAX register with the EAX register. So we're going to exchange EAX with the EAX. Does that do anything? No. No. So that is effectively a no-op. Let's see. We don't talk about the exchange instruction in here, but I just told you what it does. And the exchange is a good example of a CISC instruction, because couldn't you just do this with the regular instructions? Or actually, what does exchange do? What do we call that in data structures? Swap, right? swapping two variables. So they encoded swap into one instruction for CISC. A RISC would not do this. I mean, a couple of RISC architectures might, but general RISC would not. You'd have to copy it to a temporary, copy one value to the first one, and then copy your temporary back to the second one. So that'd be 3 instructions to do what this one will do in one instruction. Now, there are pros and cons to both those approaches. With having more instructions, it's way more complicated and your hardware is more complicated. But you will hopefully have fewer instructions, so maybe you'll have a performance increase. RISC will have other architecture improvements that if you take advanced architecture, I can get to. All right. Let's take a break.